Reaction D with acetone. Well, there was our acetone. And remember, the whole reactivity associated with the carbonyl group is the carbon is slightly positive, the oxygen slightly negative. That slightly positive carbon attracts the nucleophile, which in this case was the N3-. So here's N3-, one possible Lewis structure of it. Lots of electrons there. One of those lone pairs comes on in to the carbon, at which point the carbon says to the oxygen, why don't you take those pi electrons and make them a lone pair in a p orbital? So it does just that, and we get this tetrahedral intermediate, which is going to become, it's already important, it's going to be more important in the next module, recognizing the tetrahedral intermediate when you get a nucleophilic attack on the carbon of a carbonyl group. And anyway, at this stage now, this O- can do all kinds of different things, but in this particular case here, we have the HCl, or I'm actually writing it as HN3, doesn't make any big difference, comes on in there. Lone pair of oxygens from that negative charge goes on the hydrogen tells effectively the N3- to get lost. And so you make the final product, and of course another N3-, which can then float around and attack another one. Ordered in terms of increasing reactivity towards nucleophilic addition, explain why. So we've got all of these nice little compounds here: ethyl-methyl ketone, ethanol, acetone, hexachloroacetone. Well, first of all, aldehydes are always more reactive than ketones because there's less bulkiness around this carbon. So that means that the one aldehyde that we have here is almost certainly going to be the most reactive. Now then we compare, first of all, this one, and there's more bulk around that carbon there. We've got an ethyl group here instead of a methyl group, harder for an attacking group to get to that carbon there. So this is probably going to be the worst one because it is the bulkiest ketone. Now looking at these two here, we've got methyl, and then we got trichloromethyl here. So you might say, well, this is a little bit bulkier than this one, so this should not be as reactive as this one. However, there's not just bulk to consider, there's also electronic effects. This carbon here with 3 chlorines and this carbon with 3 chlorines, those chlorines are sucking electrons away like a top-notch vacuum cleaner. And as they're sucking electrons away from the carbons, those carbons are going to suck electrons away from this carbon. And so this means that this carbon, which was already slightly positive because of the oxygen sucking electrons away, is going to be even more slightly positive. And seeing as how the reactivity is associated with a nucleophile coming in here, the more slightly positive this carbon is going to be, the more reactive it's going to be. So thus, for electronic effects, this one more reactive than this one. So therefore, this is the second worst, only being better than the bulkier ketone. And then this one here would be the second best. It's still a ketone, but it's a very electronegative ketone, if you like. So very slightly positive carbon there. I wouldn't, off the top of my head, want to argue that the electronegative chlorines here make this ketone more reactive than the aldehyde. I would always say the aldehyde would win out, but that's a topic for a third-year university chemistry class. So there were our aldehydes and ketones. Hope you enjoyed them. Fun chemistry, predictable chemistry, and hopefully chemistry that you now understand.